Okay, new concept. We're going to talk about matrix inverses. Now, the idea of matrix inverses, going back to ordinary algebra that you learned in high school or whatever, if you have some equation like this, 5x is equal to 7, how do you solve that? Well, you divide both sides by 5, right? And it gives you x equals 7/5. This is a nice, easy way to solve equations. Now we have equations that look like this, ax equals b, and we want to solve for x. Wouldn't it be nice if we could divide by a? Well, it turns out in some sense we can, but it's a little more complicated than in the way that you've seen before. So let's go on and see how that works. So let's take this example of a system of linear equations. Now we know how to write it as a matrix vector equation. We get the matrix of coefficients, the vector of variables, and the vector of constants. Now it turns out that there's a matrix B with special properties. You can verify that this matrix B times the original matrix A ends up giving you the identity matrix. So just for example, let's verify this entry here, this 0 here. How would you verify that? Well, that's the first row, third column. So I need to look at the first row here times the third column here. And if it's correct, I should be able to verify that I get 0 as a result. Well, here I have minus 10 times minus 12, so that's 120. Then I have minus 12 times 7, that's minus 84. And then I have minus 9 times 4, which is minus 36. And you can work that out. That actually gives you 0. And by magic, all of these entries work out, and we get the identity matrix. Now we'll find out later how to actually compute this kind of matrix. But for the moment, let's just take the fact that it does exist. All right. So if I want to solve for x here, I can take ax equals b and multiply both sides by b. Okay? If I multiply both sides by b, I need to be careful to multiply both sides by the matrix b on the left. So that gives me bax is equal to bb. Okay? But I just found out that ba is the identity. Okay, so I can replace this bax by the identity, and he calls it I3 times x, and that's equal to bb. Now, what's the identity matrix times any vector? Well, it's that same vector itself. Okay, so that's how he did the same thing, only kind of working backwards, that this vector x turns out to be this new matrix capital B times my vector of constants. So to solve this equation, ax equal b, all I have to do is take my vector of constants, multiply it by this strange, wonderful matrix B. So vector of constants times b, and I get this result. And you can verify that this x, if I take a times this x, it will give me the vector of constants b that I need. All right? So this matrix B is called the inverse of A. When they're combined, the result is the identity matrix. Okay? And so here he makes the same analogy that I made before, that this is just like dividing. Okay. All right. He also points out that in some cases there are no solutions. And in some cases, there's an infinite number of solutions. I can put in any x here and make this true. I can't put in any x in here to make that true. And what happens is, with matrices, is the same sort of thing happens. Some matrices don't have inverses, just like this 0 doesn't have an inverse. Okay, so we'll go and work through that analogy in the subsequent sections. Right. So first of all, definition. Suppose A and B are square matrices, they have to be square, such that AB is the identity and BA is the identity. Now, the identity must have n rows and n columns, because we know that the identity has the number of rows of A and the number of columns of B, and both A and B are square matrices of size n. If this is true, then A is invertible, and B is the inverse of A. We write B is equal to A inverse. All right, that's very plausible. Now notice that if B is the inverse of A, just the way this is written, I could also say that A is the inverse of B. Or we could just say A and B are inverses of each other. Not every square matrix has an inverse. One example is the zero matrix, 0, 0, 0, 0. Now, if I multiply this matrix by any other matrix, I'm going to get the zero matrix. So there's no way for me to find a matrix that multiplies by this and gets me the identity. So the zero matrix has no inverse. Just the same way that the zero itself has no multiplicative inverse. You can't multiply the number 0 by anything and get 1. Now there are other examples of matrices that have no inverse, and we'll see some examples right here. All right, so consider this coefficient matrix. Now suppose that A is invertible and had an inverse, say B. Then if I chose this vector of constants, then this inverse matrix B times this constant vector B would be a solution of AX equal B, just like we saw before. But AX equal B has no solution. So that means the inverse B cannot exist. So no B inverse can exist. Okay? Because if there was an inverse, then I could find a solution for X. Okay. All right, so we say that the fact, assuming that A has an inverse leads to an inconsistency. So there's no way that B could possibly exist, because that leads me into a brick wall, dead end, that can't possibly be true. Okay, so let's look at one more example. Here we have two matrices out of the blue. And if you do the multiplication by hand or using Sage, you end up with the identity matrix. And strangely enough, if you do the multiplication the other way around, you also end up with the identity matrix. Okay. So now we're going to go into trying to figure out how to find the inverse of a matrix. As he says here, we're not going to try to figure out just yet when an inverse exists, but we're going to try to figure out how to find the inverse of a matrix. Before I close, I will point out that there's one point here that should be mentioned. Here we say that in this definition it says B is the inverse of A. Technically, there might be more than one B that serves as an inverse. So really this should be B is n inverse of A, because you could possibly have more than one. It turns out that there is a unique inverse whenever the inverse exists. But at this point, we can't tell whether there might be several inverses of A. Okay,